Uh, Good morning, everyone. We are recording now. And just to remind you that there's no class next Monday, it's Memorial Day. Uh, Pace wise, we are doing pretty well. I just assigned a new homework today that is homework two. There's plenty of problems, but they are short. So please, you have till next Friday to get them done. So please start working on them. Or Thursday, I'm not sure. Check the date. All right, any questions before I start?
I have a quick question on
Yes.
one of the current problems on the homework. Um, and just making sure I'm understanding what the problem is asking for.
Okay.
Um, I'll let you grab the book and then I'll ask it.
No, go ahead. Tell me which problem.
Um, Problem 1.3 says find the escape time of solutions to x prime equals x squared, blah, blah, blah. I just want to make sure that we should interpret x as position and therefore x prime as velocity,
Uh,
as opposed to x being velocity already. I just want to make sure, since that's not said.
1.3, find the
1.3.
escape time, yeah, of the solution. So basically, escape time is when the solution goes unbounded.
Okay,
You know what I mean? So you're going to have something in the denominator, or you know what I mean?
sure.
And then for what value of t, the solution jump and growth becomes unbounded. This is what the escape time is.
Okay,
All right,
thanks.
no problem. Other question. All right. I hope you are reading the book, and I would welcome feedback by email or anything, because I think I will be, in a year or two, I will be doing the second edition of it, adding new problems, changing materials around, and so forth. All right. So now we're going to be in chapter three, and this is the beginning of systems of differential equation. All right. Because most of the, I mean, a second order differential equation can be put into a system. All right. This is what we mean by that. So let's consider x second of t plus at x of t equals 0. So this equation, this appears in mechanical vibration, or pendulum, okay, or a pendulum with small angle change. All right. So, I mean, you've seen a second order, the variation in the spring problem can be written like that. Since AT is positive, so this gives you an oscillation. The solution will oscillate because it's going to be in terms of sine and cosine. All right. So if we let x1 equal x, that is the displacement, and x2 equal x prime, that is the velocity, then we get x1 prime equal x prime, that is x2, and x2 prime equal x second. And from here, that is minus atx, and that is minus atx1. So we arrive at the system x1 prime equal x2 and x2 prime equal minus atx1. So that is a system, you see? And so I mean, we're assuming that AT is positive and continuous. In the book, I have A squared for a reason, but it doesn't really matter. All right. So this is what we have here. And so we see we can put it into a system. So hence, we look at the general system x1 prime equal f of st x1 x2 xn x2 prime equal f2 t x1 x2 xn and xn prime equal fn of t x1 x2 xn. Okay? Now, if we let big X equal x1, x2, xn, then we may write x prime equal f of tx. This can be written like that. If we let capital X and I put horizontal line on top and the bottom to distinguish it from this because I do not trust my handwriting. Okay? All right. So now everything we did in chapters 1 and 2 carries over to this system. .12. All right. I'm talking about in term existence and uniqueness. All right. Existence and uniqueness. So of course you will need Lipschitz conditions, and they all carry over the same way. Okay. And then we arrive at theorem 3.12, which is always all the same. So we will have, again, for this system, we're gonna x prime f of tx, and we're gonna define xt naught equal the vector x naught. And then Lipschitz condition would be f of tx minus f of ty is less or equal to k of x minus y. Okay? So this will be a Lipschitz condition, and everything else, and your set D is a subset of R cross Rn. This is a subset D in the proof of the other theorems, if you need it. And this is mean for Tx, Ty, belong to D. It depends. So whether you have a globally Lipschitz or you have a locally Lipschitz and so forth. All right? And you will define a norm, appropriate norm, to carry on with the conversation, with the lectures. All right. And let's say, let's take f of tx. So I want to go back and here on a set D, which is including in R cross R. So this is a scalar function. All right. So let's say we said Lipschitz. So what is the Lipschitz condition? We're going to have for f of tx1 minus f of tx2. Remember this, what this is. This is equal to f prime of c times, or let me drop the absolute value. F prime of c x2 minus x1 for, okay, for c in x1, x2. Can anybody tell me why is that true? What do you think? And f prime, this mean del f over del x at c, because we have t here. Can anybody tell me why? This is by the mean value theorem. So if I take the maximum norm, I'll get f of tx1 minus f of tx2 is less or equal to del f over del x at c times x2 minus x1. So this is your Lipschitz constant. So if del f over del x is bounded on D, then f is Lipschitz. With Lipschitz constant, k equal to del f over del x at some number c, which is the maximum. Okay? All right? So this is another way of finding the constant. And why is that important? This is important when you have a problem like let's take a look at f of tx equal t over 1 plus t squared, or let's say, I really don't care, 1 over 1 plus t squared sine x of t. So if you want to show this is Lipschitz, so we're going to get, let x1, x2 belong to the set D, and here it is R cross R. Or may I say tx1, tx2 belong to D, then I'm going to have f of tx1 minus f of tx2 is equal to 1 over 1 plus t squared sine x1 minus sine x2. All right. So this is less or equal to sine x1 minus sine x2 because this is less or equal to 1 for all t. Now, by the mean value theorem, this is equal to del of sine x over del x. This is less or equal to times x1 minus x2. Okay? And so this is equal to cosine x from x1 minus x2. This is less or equal to 1 times x1 minus x2. So k is 1. Because cosine x is always less in absolute value, less or equal to 1. So you see how you show this is Lipschitz? Okay? All right. I don't want to dwell on this one too much. Okay, I'm looking just back at the chapter. All right. Okay. So we established that okay, so now let's take a look at, I'm on page 61 now. So let's take a look at the nth order differential equation equal to g tx x prime x to the n minus 1. So I'm going to do the change of variable. Okay. xi of t equal to x I minus 1 of t. Okay. For I equal 1, 2, all the way to n. So why don't you go ahead and try to convert this into a system if you can. Go ahead. So if you take I equal 1, you get x1 equal to x. You see, when you have xi minus 1, mean for I equal 1, x or 0 equal x. That means there is no derivative. I equal to 2, you get x2 equal x prime. Okay? And so forth. Xn, you get, I equal to n, xn equal to x to n minus 1 of t. Okay? So x1 equal to x, x2 equal to x prime, and so forth. So this one, you're going to end up with, this is going to end up with x1 prime equal x2, x2 prime equal x3, and xn prime equal to g of t x1 of xn t. Okay? So if you do the correct change of variable. All right? Because you see here, when you look here, x1 prime equal x prime, but that is x2. And same thing here. You look at x2 prime equal to x second, and x second equal to x3. Okay? And so forth. And you go down the list. All right? Okay, so this is in a vector notation. Let's take a look at an example. So let's consider x third of t plus t, 3t plus 1, x second plus x prime plus 4 t squared x equal to sine 2t. Okay? So the idea is to take xi of t equal xi minus 1 of t, and for I equal 1, 2, and 3. Okay? And therefore, for I equal 1, x1 of t equal to x0 of t equal to x of t. I equal to 2, x2 of t equal to x prime of t. and I equal 3, x3 of t equal x second of t. Well, this is not the end of it. Now you need x1 prime. So x1 prime of t is x prime of t, but x prime of t is x2 of t. And from here, you get x2 prime of t equal x second of t, but x second of t equal x3 of t. And from here, you get x3 prime of t equal x third of t. Well, now we need to go back here. That is minus 3t plus 1 x second minus x prime minus 4t squared x plus sine 2t, and that is minus 3 times t plus 1. What is x second? X second equal x3 minus x prime is x2 minus 4t squared x is x1 plus sine 2t. So there is your system. So the system is x1 prime of t equal x2 of t, x2 prime of t equal x3 of t, and x3 prime of t equal to minus 4t squared x1 of t minus x2 of t and minus 3t plus 1 x3 of t plus the function sine 2t. Okay, so that is your system. So basically, this will be your f1, this is your f2, and this is your f3. Okay? All right. That's enough of that. All right. And there are a couple theorems I need you to read in section 3.1. So finish reading section 3.1. There is some valuable information there. Okay? There's some valuable information. All right, any questions?
I just had a quick question.
Yes.
Like for your eyes, how you going from like your I1, I guess, prime to like your other? It's just like for the second case, are you just doing the calculation like beforehand on like when we were going
Right.
to page
I am
61?
using this formula. I am using this formula to set my transformation, right?
Okay.
This formula will give me transformation, and based on this formula, I'll go and compute this. So once I do, this is what my transformation should be, but I always need x1 prime, x2 prime, x3 prime. That's what I always need.
Okay, so that's just that equations just used to find your prime, basically.
Right. And then you come here, you say x1 prime is x prime, but you move down, what is x prime? Is x2, right?
Okay. Yep. Thank you.
And that's how you do it.
Got it.
You do it all the way until you get to the end, to the last one. The last one, you have to go back to your original differential equation.
Awesome. Thank you.
Okay. Other questions? Usually writing a higher order differential equation into systems give you more information, and as you shall see later on. All right. I'm going to flip the board. All right, so now we're going to be in section 3.2. And the title is x prime equal ATX. So motivation. Let's take a look at so we're going to consider the linear system of ODEs of the form x1 prime equal to A11 x1 plus A12 x2, and these depend on time. I mean, all the A's depend on time. Plus A1n xn plus G1 of t. And it's same thing. X2 prime is A21 x1 plus A22 x2 plus A2n xn plus G2 of t to xn prime equal to an1 x1 plus an2 x2 plus ann xn plus gn. Okay? So we have where the function aij of t, or 1 less or equal to I less or equal to n, 1 less or equal to j less or equal to n, are continuous. Okay? And real valued function. On some interval I. Okay? So this system, the above system, can be written in the matrix form let's see what I say. In the matrix form, x prime of t equal at xt plus gt, and we're going to call it 3.21. Okay? So the above system, now I'm going to specify A and G. So I'll let you finish writing. Yeah, I'll be right back with you guys. Let's take a break for a second here. I'm gonna try to do something else. All right. Um, I'm not sure what this guy is asking me. Just give me another second. Excuse me. Excuse me. All right. So this is what we have now. So let me tell you what A and G are. Sorry for the delay. You have nice grade. Where X is X1, X2 to Xn. AT is A11, A12, A1n, A21, A22, A2n, AN1, AN2, ANN. Okay, and GT is G1, G2 to G. Okay, so this is called a non-homogeneous system. All right. Okay. Any questions? So we're going to be working with this system for a while. Okay. And okay. So definition, we say the n by 1 vector y is a solution, is a solution of 3.2.1 on I if y is continuously differentiable on I, and y prime of t equal to at yt plus gt for all t in I. So it has to be differentiable and satisfies this differential equation. All right. Okay. Any questions?
Sure, I have one.
Yeah.
This isn't something you wrote on the board, but rather is in the book. It says we denote the space of n tuple continuously differentiable functions. What's a tuple?
Oh, tuple mean if you have a function like that, this is tuple. It has
Okay.
more than one component.
Gotcha. Never heard that before. Thanks.
Oh yeah, yeah, yeah. We use that a lot. Yeah. All right. So now let's take a look at the norm of a matrix before we can do any work. I want you to know that this system is non-homogeneous because of this one. It's non-homogeneous. And if you put y equals 0, you get 0 equals 0. If gt equals 0, then it's homogeneous. All right? So this is a non-homogeneous system. But we're going to have to use a homogeneous system to get to the non-homogeneous. All right? Okay. This is definition of 3.2.2. Okay? Hello? Did I what? No. Who is this anyway? No, no, I really didn't call you or didn't call anybody like that. I really didn't. I'm sorry. Okay. All right. A norm of a square matrix A is a non-negative real number denoted by A, okay? There are several ways to define A, but all must satisfy the following. One, the matrix A is bigger or equal to 0 for any square matrix. 2, A equals 0 if and only if A is a 0 matrix. 3, alpha A is alpha times A. Alpha belong to R. And 4, A plus B is less or equal to A plus B. Or B is a square matrix. So this is the norm of a matrix. It's like similar to the norm of a vector. All right. Any questions? So here is an example 3.3. So let's take A equal Aij. So this is a matrix. Okay. I 1 less or equal to I less or equal to N, 1 less or equal to J less or equal to N. So this is called A, the one norm, and is given by A1 is maximum 1 less or equal to J less or equal to N of I equal 1 to N Aij. And this is called the maximum absolute column. Okay. So this is the first norm. All right. So basically, you've taken the column of the matrix and you're adding all the entries. To the infinity norm, and this is denoted by A infinity, and this is the max of I between 1 and N of J equal 1 to N Aij. Okay, this is the maximum of the sum of the absolute value along each row. Of each row. Okay. So basically what you do is you sum all the rows and whoever gives you the biggest value, take it. So for example, if A equal minus 1, 1, 2, 1, then the A infinity is the max between minus 1 plus 1 and 2 plus 1. Of course, that is going to be 3. Okay? All right? Okay? And now the Euclidean norm, the Euclidean norm, and that is denoted by AE is I equal 1 to N, J equal 1 to N, Aij squared. So basically, you're summing all the entries in the matrix. So for example, for AE, here is -1, +1, +2, +1, and that is 2 to 4, that is 5. Okay. Any questions? All right. Now let's do another thing. Now that we have defined the norm of a matrix, let's prove a theorem. Okay. This is theorem 3.2.1. So we have recall that x prime is atx plus g of t, and this is 3.2.1. All right. So suppose AT and GT are continuous on some interval a less or equal to t less or equal to b. Then 3.1 has a unique solution phi t on the interval a less or equal to t less or equal to b with phi of t naught equal to eta, where t naught is in A and B. So this is an initial function. So this is an initial point. Okay? Any questions so far? proof. Let the matrix A be any suitable norm, matrix norm. Okay. Let K2 is the max of A less or equal to T less or equal to B of G of T, and K1 equal to the absolute value of eta, whatever eta is. Okay. Let K3 equal to the max of A less or equal to T less or equal to B of AT. So that is a norm, basically. Okay. All right. Then, now, we know now the solution, let phi of t be a solution on AB of 3.21 with phi of t naught equal eta. Then phi of t is eta plus t naught to t of as xs plus gs ds. Okay, where a less or equal to t less or equal to b. All right. All right. So let's take absolute value, take the norm. So we're gonna have phi of t less or equal to eta plus t0 to t as x of s plus ds plus t0 to t g of s ds. All right. We'll write down this formula. Okay. So I'm gonna try to do some minimization. So we have t0 to t g of s ds. This is less or equal to t0 to t maximum A less or equal to T less or equal to B of G of S ds. Well, that is less or equal to, what is a GS? The maximum of G is K2. Less or equal to K2 T0 to T ds, less or equal to K2 T minus T naught, less or equal to K2 B minus T naught. Remember, T is between A and B. All right? Lily? Nancy? 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 Please come. Come. All right. And so, phi of T less or equal to A dot is K1 a plus K2B minus T naught a plus, I still have T naught to T of the max of S between A and B of AS ds. Sorry, X of S ds. So this less or equal to K1 plus K2B minus T naught plus the maximum of this is K3 plus T naught to T of K3 X of S ds. So we're going to use Gronwall inequality. Sorry, this is not, this is phi. I've been using X. This is phi. Oh, again, this is phi here. Me bad. Phi, wow. Domino effect. Okay? These are all phis. Then, by Gronwall's inequality, we have that phi of T is less or equal to K1 plus K2B minus T naught times T naught to T, sorry, find the exponential of T naught to T of K3 ds. Okay? And that is less or equal to K1 plus K2B minus T naught E of T minus T naught ds, sorry, not ds, and that is less or equal to K1 plus K2B minus T naught times, and I mean by this all. This is the whole thing. E to the B minus T naught. So this is less or equal to some constant L. So the solutions are bounded. So taking the norm, so we will see that the norm of phi less or equal to L, and hence all solutions are bounded. Okay, all the solutions are bounded. And they're bounded on the interval AB, correct? Not everywhere, they're bounded on that interval AB. Any questions? Now, you can easily show that the solution is unique. Okay? You can easily show that the solution is unique, but we're not going to worry about it now. Okay, yes, I will show you that the solution is unique, and I will stop here. But I will be brief about it. Next, we show P is unique. Suppose we have two solutions. Phi 1 of t and phi 2 of t. Then phi 1 of t equal to eta plus t naught to t as phi 1 of s plus g of s ds, and phi 2 of t equal to eta plus t naught to t as phi 2 of s plus g of s ds. Okay? All right. Then if I look at the difference between them, then phi 2 of t minus phi 1 of t equal to t0 to t as times phi 2 of s minus phi 1 of s ds. If this will cancel out with this, and this will cancel out with this. So you're only left this one. So if I take the absolute value is less or equal to t naught to t, the max of as phi 2 of s minus phi 1 of s ds. This is less or equal to, what is the max of the matrix? Is K3 t naught to t phi 2 of s minus phi 1 of s ds. And so by Grunwald's inequality, I have phi 2 of t minus phi 1 of t less or equal to 0 times e to the k3 t naught to t ds. So that is equal to 0. So that means this is if and only if phi 2 of t equal phi 1 of t for all t belong to A. So this shows the solution is unique. So you see how important Grunwald's inequality is? It gives you boundedness, it gives you uniqueness. Boundedness means existence of solution too. Okay? So I'm going to stop here and we'll pick it up next Tuesday. So please work on your homework. I will grade your homework this weekend and so forth. All right. Thank you very much. Do you have any questions before I log off? Somebody has a chat.
I had a quick question about the second homework.
Please.
So for the homework problems you assign, I just wanted to verify that theirs was two of the, it shows like 2.3 and then 1 through 4. Is that supposed to be like 2.2?
Let me take a look here for a second.
Because you have two of them that say 2.3.
So what do I say? I say 2.3, then what?
You just have 2.3 listed twice.
Well, I mean, okay. So I think what I meant to say is 2.1, 2.2,
Okay.
and 2.3. Okay? And 2.4, they were selected, maybe selected a problem for 2.4. Is that what I have? Let me stay with me online. I'm going to escape here. Let me go to my canvas. Okay, I'm almost there. Stay with me. Okay. I'm under the assignment now. Homework 2. Okay, I have, I meant 2.4. Okay. So section 2.6, number 2.1, 2.3, 1 and 4, part 1 and part 4, and then 2.4. Okay, I'm going to edit it. I'm going to make the changes now. All right. Ugh. All right. I made the changes. Okay. All right. Any other questions? All right. Okay, I'm going to stop recording.
There was one last comment. It was in the chat. It